So next we have Jesse Hunt from Harvard CFA talking about NANCY Next Generation All Sky Near Infrared Community Survey.
All right, thank you very much. Good day already. Good day, everyone. I'm Jesse. And it's 3:30, which means it's nap time for me and for you. But just for the next 12 minutes, I would love to talk to you about what I think is one of the most exciting opportunities that Roman can provide to the astronomical community, an all-sky survey. And before we get to the details of what this all-sky survey can entail, which is very neatly detailed in a white paper with many of you in the crowd, let's just first remind ourselves of what Roman is capable of. At the very base, Roman is an incredible imager that can deliver images with 0.1 arc second resolution in the infrared. So how does this compare to already existing all-sky infrared surveys, such as 2MASS and WISE? 2MASS goes down to 16th magnitude in the J and H band, and it is a ground-based mission, so it is limited in resolution by ground-based astronomy. WISE, on the other hand, is a space-based mission. It goes a little deeper. It goes into 18th magnitude in W1, but it's a smaller telescope, so it has an angular resolution about 6 arc seconds. But given these specs, the impact that these surveys have had on astronomy is immeasurable. And as a very crude attempt to try to convince you that this is very impactful for astronomy, I just screen grabbed the citation numbers for the survey papers, and they're on the orders of 10,000. And according to Reddit, there's only 10,000 living astronomers at a time, so that's a very big number. And the point here is that Roman can and really should go much deeper than these surveys. In fact, it's very feasible to reach 25 magnitudes over the entire sky at 0.1 arc seconds with Roman. And just to remind you, that's more than order of magnitude, approaching 2 orders of magnitude in both dimensions of resolution and depth compared to existing IR all-sky surveys. So what do we do if we have an all-sky survey? The answer is everything, obviously. But to limit ourselves to 12 minutes, let's talk about some concrete examples, right? So I think one of the most obvious first things to do would be to cross-correlate, cross-match, and cross-analyze with basically every planned and future and current surveys, some of which are LSST, Rubin, SphereX, DESI, Euclid, the list goes on and on and on. So what's a specific example? Let's take Rubin, let's take LSST. As we all know, LSST is going to be truly transformative. It's going to image half the sky between 24 and 26 magnitudes in depth, depending on your exact filter, right? And at the core of its mission, it wants to solve cosmology and it wants to solve galactic science. However, there is a big caveat to this, which is the faintest galaxies and the smallest stars and the faintest stars actually blend in together at these faint magnitudes. So according to this study done by Slater et al., sort of solving the star-galaxy separation shows you exactly this problem. So on the x-axis is my scrolling bar. Oh, goodness. On the x-axis is the limiting magnitude of the survey at phi sigma. And on the y-axis is the so-called star-galaxy separation limit. And you can think of this as the magnitude at which you're confident that you can very much select stars against galaxies. And the different lines indicate different levels of seeing. So let's take the blue line. Full width half max of 0.7 arc seconds of seeing. That's phenomenal, right? But given that blue line and given a limiting magnitude of 25, you're still confused whether or not your source is a star or galaxy at 22.2 magnitudes. So between that number and 25 mags, you're limited by this confusion. How do you solve this? I'm glad you asked. With a 0.1 arc second resolution image of the entire night sky with Roman. So this is an example where Roman can truly enable a new expansive science with an instrument that will be operating at the same time. Talking about galactic science, which is where I come from, Roman can also in itself enable a completely new phase of discovery with this all-sky survey. So assuming that we have a reference epoch of the entire night sky, we can then follow up with it at the end of the 5-year baseline mission, which will give you proper motion uncertainties that can measure every single star within the galaxy and beyond the galaxy. Now, that's only a bit of a stretch, and here's why. Take red clumps, a very famous standard candle. A red clump star at 25th magnitude in the white filter is at 250 kpc in our galaxy. That is the virial radius of the Milky Way. And if that star moves, we will be able to resolve its motions. And just following up that red giant branch, if you go to the tip of the red giant, you can see the tip of the red giant out to 10 megaparsecs. That's the entirety of the local volume. So all this to say, if you have an all-sky survey that has 2 epochs and can measure proper motions, you will have at hand a discovery machine for local dark matter substructure. And for those of you not familiar with this field, there's an entire industry behind using proper motions to select very cleanly these thin stellar streams or cold stellar streams to look for impacts from predictions of lambda CDM, which are these dark matter subhalos. And this is proving to be a very promising avenue for searching for the particle nature of dark matter in our own galactic backyard. Not bad. All right, so you can solve Roman, you can solve Rubin, and then you can solve dark matter. Brilliant. What else? Everything else. A big reason why I decided to come here today was so that I can learn from you and listen what other all-sky science cases you all have. So please do come find me in the coffee hours or the beer hours, and I would love to just hear what your thoughts are. All right, so now that the soap opera is done, let's talk about some numbers, yeah? So here are 3 sort of unbreakable curses of the all-sky survey. You gotta have at least 1 band. You gotta have at least a single epoch. And you gotta have a magnitude that is at least deeper than 25. And this is largely motivated by the fact that if you go shallower than this, then you're just entirely overhead land. You might notice that there's not a 4th parameter, which is footprint, because I fundamentally believe that an all-sky survey is different from a kind of an all-sky survey. All right, so we can play with some of these numbers and some of these parameters. So on the right-hand side, I'm showing you all the filters in the Whitefield instrument that we can perform this survey with. And on the x-axis, I'm showing the time that it takes to reach 25 magnitudes in AB. The blue filters are in blue. The redder filters are in, well, red. The 2 things that stick out among the red filters are, of course, one, the F146, the wide light bucket. That is by far the fastest filter you can use to map the whole sky. And then there's another one, the H-band, F158. Let's still consider that one as well for now, for the sake of the argument. For the single epoch parameter, right? Again, the minimum you want to do is have 1 epoch. But if you can add a 2nd epoch at the end of the mission, what do you gain? Everything. You gain proper motions, and then you also have an opportunity to add colors, because then you can select a different filter. So there is really something to consider here. So if you propagate this into the full sky, here's the big numbers. So in the F146, you can hit 25 mags in 30 seconds. In H-band, you can hit it in 60 seconds. This means for the very fastest all-sky survey you can do, you can perform that in over 120 days with the wideband filter, or 107 days with the H-band filter. And if you follow a more traditional 2 chip gap dithers, that number increases, of course, to 184, most of which is overhead, or 235 days with the narrowband filter. So these are sort of the 2 extremes, right? In one case, you just forego dithering entirely. The other case, you get your nice, beautiful 3 dithers. So the real sort of strategy is going to be somewhere in between that, between 120 and 184 days. So that's not the only things that we want to consider, right? So here's some further considerations, not limitations, but just things to consider. It is really imperative to image the entire sky in 1 epoch and 1 band as soon as possible. And that is because then we set ourselves up for success in the proper motion measurements at the end of 5 years, hopefully 10 years. The second thing to consider is it really would be prudent to image at least the Rubin footprint as early as possible as well, for maximum synergy. And that comes down to around 20,000 square degrees, which could be done entirely in 2 months. Or if you limit yourself to the cosmology footprint, that becomes around 30 days or about a month. And lastly, the all-sky survey is not a monolithic thing that exists outside of all the other Roman projects. In fact, we already have 2 amazing down payments on the full sky, namely the Galactic Plane Survey and the High Latitude Wide Area Survey. And if you leverage these 2 surveys as a means to eat up the entire 4-pi sky, then you can really have a synergy between the core community surveys and a potential all-sky survey. So with that, I would like to at least give you some takeaways, right? The first thing is Roman poses a unique opportunity to image the entire night sky at 0.1 arcsecond resolution down to 25 magnitudes, and there's nothing else on the horizon that can do this. This is our shot. This would, of course, add an immense legacy value to Roman, in addition to enabling all sorts of other science with every other mission that is going to come about. And all this for a hefty package of 100 to 200 days, which is really not much if you think about the impact it can have on the scientific community. So with that, I would like to end with a QR code to the white paper that you can freely read. Or even better, I'm here in person form. So please come up to me and ask any questions that you'd like. Thank you.
Thank you, Jesse. Any questions?
Thanks, Jesse. This is maybe more of a question for Julie and Jeff and other folks. But this is for like a point and stare type mission or a point and stare type survey, right? I mean, so with C3IR had the ability to do dash mode observing, where you sort of allow the telescope to sort of drift scan and you decouple the up the ramp sampling to chew up more area at the expense of sensitivity. And so that found that you would go maybe 1 to 2 magnitudes shallower. So if Roman were able to do this sort of dash mode at the expense of maybe only reaching 23rd magnitude in H, would that still be sufficient? And is that something that the telescope could be made to do?
Oh, is it, that could be like, that's like between.
That's the dual question for the lot of you all.
What I'm going to say is 23 is very much larger than 18. So yes, it'll be amazing. Yeah.
So the short answer is that our target acquisition time is measured in seconds. So you don't really save the overhead by not acquiring. You might as well just acquire.
Other questions?
Thank you for the interesting talk. And so I feel you justify the needs for the special resolution and the depth and covering, large area. But I don't hear the, justification of the all sky imaging.
Oh, so you mean like, why not 39,000 degrees? Why
Yeah.
42,000 degrees?
It's just a desire to cover everything, or is there any more reason to covering the whole sky?
Well, there's a lot of reasons actually. One of which is the fact that if you want a legacy value, you don't know where future instruments are going to point at. So there is a lot of legacy value to having the entire 4-pi. If you want to do something with Sphere X, for example, then you really want all sky. And then also if you want the synergy between the northern telescopes and the southern telescopes, then you also want all sky. So you can find zones you want to avoid, but that really is limiting the future trees that can grow, right? And that'll save you maybe like 30 days off of 120. Like, the question does come down to, is that investment going to be worth having the entire sky down to the same magnitude? And I think the answer is yes.
Maybe one last question, and then we'll move on to the last speaker.
Thanks. Excellent talk. I guess I had a question that was part programmatic and part scientific. So of course the full 4 pi of the sky contains a number of different science cases from different communities. And that's both part of why it's so exciting. And it's also part of why neither an extragalactic sort of program or a cosmology program or a Milky Way structure program is necessarily going to go do this on its own. Even though some may do pieces of it. So I guess my science question is how important is it to you that the different parts of the sky be covered in the same way, either to comparable depth, comparable coverage, time baseline, whatever, versus do you think the opportunity is mostly do an all sky survey and it could be stitched together from different components?
Thanks for the great question. So personally, coming from a galactic science background point of view, I think the point of having an all sky for me is if there is dark matter substructure out there that is disrupting cold stellar streams, you're going to find it in the all sky. And you want the coverage to be at least uniform to the point that you're not inducing severe selection effects into your analysis. So in terms of detecting these thin stellar streams with proper motions and finding gaps and comparing it to dark matter models, you really want full coverage of the entire galaxy. So for me, there's a value to all sky. For other science cases, of course, it'll have to be worked out individually. Yeah.
Okay, let's thank Jesse again.